In this conference series, we aim to discuss about sustainability in the framework of today's changing paradigms, and also to think about environmental effects of architecture, as well as actual proposals for a healthier future. Today, we will start with a keynote speech by our special guest, John Straube. Let me introduce him briefly. He is an associate professor, joint appointed to the Department of Civil and Environmental Engineering and the School of Architecture at the University of Waterloo. He researches and teaches building science, building materials, and engineering design with a focus on high-performance, low-energy sustainable buildings. He's also a principal at RDH Building Science, where he leads forensic investigations, hydrothermal measurement and analysis research projects and design projects in the areas of low-energy building design, highly durable building enclosures, new building materials and systems, and extreme climate buildings. Professor Straube authored high-performance enclosures and co-authored building science for building enclosures with Eric Burnett. He received the Lifetime Achievement Award in Building Science Education from the National Consortium of Housing Research Centers. It's a great pleasure to have him as our keynote speaker, and we would like to thank him for his valuable participation. Now, he's going to talk about designing the buildings of the future with the reality of changing climate. Please join me in welcoming Dr. John Straube. Thank you.
Thank you, Banu, and thank you to everyone who's organized this conference for inviting me. It's quite an honor. I'm hoping that today I'm going to introduce you to some of the, I guess, technical approaches to how we can build better buildings in the future that acknowledge the challenges that we face in front of us. Edward Masria spoke last time about the absolute urgency of doing something about reducing our carbon emissions. And my talk, I'm trying to tell you, what can we, those of us in the building industry who are designing new buildings, renovating existing buildings, what can we do in our practices to go towards reducing carbon emissions and responding to the fact that the world is changing around us? So, although reducing carbon emissions is an absolute urgency right now, and probably will for the next 50 years, at the same time, we have to reduce our resource consumption. There are more billions on the planet every decade, and we need to manage how many resources we use effectively and efficiently so that the planet cannot be used up in the construction of our buildings. At the same time, we want to improve the quality of the air both within our buildings and outside them, particularly in cities. And one of the things that we need to respond to is this drive to lighter, faster, and cheaper buildings. Lighter, faster, and cheaper buildings may be seen as a negative, but actually are directly responding to resource use and minimizing the resource use, hence lighter. And faster and cheaper responds to just the growing demand of the world's people for better housing, better schools, more expanded opportunities for hospitals, and so on. So the changes in the world around us really just demand that we make changes in what we're doing. It's not possible for us to continue building in the same ways with the same materials as we have for the last 50 years if we're looking to get a different result, if we're looking to produce a built world that is healthier, impacts the environment level less, and emits less carbon. So we're going to have to make changes. And this talk is trying to guide your thinking about how could you make changes? In what direction would you make changes to be able to respond to these growing challenges? So one of the things that I'm going to use as a bit of a theme to explain how we would approach the design of the envelope or the enclosure of our buildings is the inspiration that many Canadians take for how to build buildings in a harsh climate. So we can learn an awful lot for how nature has evolved to producing a polar bear that's able to survive in the far north in extreme conditions. And what we're looking at is that the way we are taking our buildings and many other large objects like ships and airplanes is that we are moving away from a solid, heavy wall structure integrated with the enclosure, the separator between indoor and outdoor, and we're moving towards a more lightweight skeleton with defined layers that provide us with the performance we want. So let me explain each of these in a bit. So the things that the polar bear does to allow it to survive in a harsh environment is like almost all large animals, it has a lightweight skeleton. It doesn't have solid bone wrapped around its entire building. It is just a skeleton structure. Then over that, there is an air and watertight skin. And the job of that air and watertight skin, of course, is to be air and watertight. And then outside of that, we have insulation. This is a different arrangement than many of the world's buildings, but it is an arrangement that has increasingly become the standard approach in North America and further afield. I've had the opportunity to work in places like China and Japan, Cuba and Bolivia, and of course spent some years in Europe, particularly Germany. And in all of these places, we now see trends towards this approach that I'm going to describe in more detail, where we look to lighten up the structure of the building, use the materials the most efficiently as possible, an air and watertight skin, exterior insulation, often fuzzy, just like the polar bears. And then because, unlike the polar bear, we care more about our looks, we're going to wrap that entire thing with finishes of claddings of various type. And I'm going to go work my way through each of those concepts here with a little bit more detail. And because humans are not evolved to live in harsh climates, what we would do in a cold climate anyway is, as humans, we add those layers. We have an air and watertight skin. We have a lightweight skeleton, but we don't have enough insulation on the outside. So we tend to add insulation, and then we provide some sort of fashion over top of that that can withstand sun and rain and shed the water off, so that we have the flexibility of as many types of different outer jackets as we like. So to start with, let's talk about what lightweight skins look like. This, for example, is the skeleton of a bear. This is a more traditional kind of building, quote, skeleton that we may have used in many buildings in the past. The masonry and the concrete here combine the job of being structure, as well as stopping air, as well as stopping water, as well as stopping the flow of heat. And therefore, we use a lot of material in a building system like this that isn't there for structure reasons, isn't there to hold the building up. We actually have to use thicker and thicker layers of masonry, for example, to provide modern levels of thermal performance. And as a consequence of that, we see a trend towards separating out the skeleton and making it just do the job of resisting loads like wind and earthquake and snow and people. So while the building industry is beginning to embrace this idea, other large industrially made products, such as ships, have already been doing this for a century. Depending on whether you're talking about wooden ships or steel ships, the transition occurred at a different time. But we want solid wood to form the hulls of our ships, Today, for any type of size of ship, we actually use a framework where we put a thin sheathing over top of it. In this example, steel plate. So those frames are spaced at specific distances. And the frames on the Titanic, for example, were spaced about 0.9 meters on center. When we moved to aircraft construction as an industrial society, we also very quickly moved to a structurally and materially efficient system, which is studs, thin sheathing on the outside, and achieving a very airtight assembly, lightweight assembly. So this is something that it would now be just a completely standard approach to how you would do aircraft construction. So in a very similar manner, the transition happened later certainly it's been only going on for 30 to 50 years in North America. But today, in any kind of larger commercial building, the most common exterior enclosure structure is what's called a cold form steel, light gauge steel, different words for the same thing. And again, what's happening is that we are limiting the amount of steel we use to the very minimum needed to resist wind, to resist seismic, etc. And so that framework is fine structurally. In the bottom of this image, we then have what's called sheathing. We'll come back to that, but something to make the wall flat. There are a number of products we can use. And this is then integrated into a structural concrete, structural steel, or mass timber construction to make a lightweight, structurally efficient enclosure for your building. So many people would think of wood framing like this when they think of Canada or they think United States. This is something that comes to mind. And it is true that this is how we build the vast majority of single-family homes. However, what's been changing is a drive to use more wood in more commercial buildings. So small restaurants, schools, healthcare facilities are moving towards wood framing like this because it is actually quite effective structurally. It is relatively low cost, and it is made out of renewable building materials that don't just have low carbon emissions in their production. They actually sequester, a word used for storing carbon inside the structure itself. So if these trees are replanted, and by and large in North America, when a tree is cut down, it is replanted, then we can actually call this a negative carbon decision because we are actually storing the carbon that would have been released in that tree in the structure of this building and holding it here for the next 75 to 150 years. Now, another framework structure that many of you would have seen, and something that came about after the Second World War, is also a light and efficient frame. That is the aluminum curtain wall. But the challenge with the aluminum curtain wall is that it has very high carbon content, both in its manufacture, but more importantly, in its operation. Modern curtain walls have very poor thermal performance. Even the best of the products available on the market have a third to a quarter of the thermal performance of a relatively straightforward opaque wall. And that means that we're seeing a change in the architecture in North America as designers respond to the need to limit energy use and to minimize carbon emissions. And we're seeing the all glass curtain wall building slowly die out and more innovative and creative design solutions being substituted, some of which I'll show you. So some of the trends that we see is that this is a example of a building of 3 stories of residential construction on top of a commercial institutional type of use below on the ground floor. So on that floor that faces the street, there will be restaurants and shops and even things like daycares and bicycle repair facilities. And then on top of this, we have apartments for people to live. And it has been become a trend in that we are seeing literally thousands of buildings of this type being built now in North America, where there's a concrete first floor which provides good sound separation, good fire separation. And then on top of that, what's called a podium, we build a wood frame building of 3, 4, even 5 stories on top. And these have the advantage, again, of sequestering, storing carbon in the building materials themselves. And we are seeing more in larger wood buildings, although not always in the way people think. So there is an interest in demonstration projects which build high-rise buildings all out of wood. But in practice, following the more economic rules, what we're finding, and certainly in my consulting practice, this is a project that we've worked on in British Columbia. It's almost 5 years old now. The best solution was always a mixed solution. Yes, we used lots of wood. Those floors are between 17 and 21 centimeters of solid wood in this 20-story building. The columns are solid wood, but the central core that contains the elevators, the fire escape passages, and resists the seismic lateral loads, that's all made out of concrete, as many modern buildings would. And then the enclosure, it doesn't look like it because it has a thin veneer of wood on it, is actually made of light gauge steel stud, following the principles of the polar bear. Then outside of that is a membrane, then insulation, and only then is the cladding. So these are being built more like this because they follow more economics than forcing us to choose only wood or only concrete for all components. So I want to spend the rest of the talk drilling down, focusing on the skin of the building, the enclosure or the building envelope. So on the right-hand side, I'm showing you an image of how we would arrange the ideal building enclosure, the perfect wall. And it is the polar bear principles. The polar bear may not have an exterior finish because they're not vain, but we're going to put a cladding on the outside, not just for aesthetics, but also often to improve solar resistance and rainwater penetration resistance. But most of the work of the building enclosure, the thing that separates the outdoors from the indoors, are these layers that are hidden from view. The water, air, and vapor control, that blue layer that resists the flow of water, air, and water vapor, is put inside of a layer of moisture-tolerant insulation, such as stone wool, expanded polystyrene, and various other such products. So the reason we place that membrane there is that membrane's really important, and so it is good to protect it from both temperature extremes and the sun. And then on the inside of all of that, we put the support structure, that lightweight frame or not, that is what's resisting wind and earthquake loads. And that now structure is so well protected from weather that it has an indefinite lifespan. It can easily last centuries because it's being kept inside the building at room temperature. Now, the list of functions that we ask for of our building skins is, the first one is that support, is to be able to resist wind load and window washers and children thrown against the inside of the building. And the next layers are the air and the water control layers. And then there's the thermal control layers. And finally, depending on the kind of building, fire and even sound is added to the list of requirements. And what's changed in the last 50 years for building enclosures is very much what's changed in people's clothing choices. We've actually become very specific in that we provide a layer or a system or a product that meets each of those requirements. And so we separate out the exact right support layer for our project, the exact right air and water membrane for our project, the right kind and thickness of insulation, and the right kind and thickness of fire protection. And that allows us, that mix and match opportunity gives us the most flexibility to directly meet the needs of our project. Now, core to a durable and functional building enclosure is an air and watertight skin. A polar bear, you rarely get to see that. And it's the same with a building. We don't get to see that because it's hidden underneath the insulation. Nice and white insulation in this case. So in practice, if I take that drawing I showed you, the partie of how we would arrange layers, and I add some more details on the right-hand side, this is still not a complete drawing on the right because I haven't shown you the cladding. And there are reasons I haven't, I'll describe in a moment. But this is an example of using a concrete structure with a lightweight steel frame system, steel studs, to be the enclosure support. And then I have insulation and air and water membranes that I layer on top. And this concept, if we look at the wall, of the gray on the right being the support structure, the blue layer in this case being the insulation layer, and the pinkish layer on the left being the cladding, it applies whether I'm doing a wall, or if I take that wall and I tilt it on its back and I make a roof, or if I take that wall and tilt it on its face and make a floor slab. So the same concepts apply. And this is one of the powers of the methodology and the approach I'm describing, is that it has very universal appeal. It can be used for many building materials, many different types of buildings, many different types of climates. So the roof is very similar in concept to the wall. And that means that we have the roof support structure, which could be wood, steel, concrete. Then we have that heavy black line, which is the air and water control layer. Then we have the blue, which is the thermal control layer. And on top of that, we put an exterior finish or cladding, if you will, which has to have sufficient weight to stop the insulation from blowing away. So this is exactly the same approach to the wall, slightly different choices for materials, though, to respond to the needs. So what I'm showing you here is a simple section through a very simple building. I've asked my engineering class to come up with a building, and they've made a rectangular gray building with no windows. So how would I put a building enclosure on this? Well, we know how we apply the wall, and that's pretty straightforward. But I've just shown you how you do the roof. It's the same idea with a different selection for materials to meet the more demanding requirements of lying on your back. For the slab, we would do the same thing. There is no finish, but we often need some way of adapting for the ground level being not flat, and that may be done with stones or polymeric sheets. And then we have to connect the dots. This is where architects come in. This is where we need to come up with a design that connects the wall materials to the roof materials in a way that leaves no voids and openings. Because where we see problems in performance, both energy performance that wastes carbon, airflow control performance that not only wastes carbon, but it causes air quality problems, but also from rain penetration causing durability issues, is a lack of continuity. These air, water, and thermal membranes need to be continuous all the way around the building. No holes, no penetrations of the insulation, if you can avoid it, no penetrations of the water control, no penetrations of the air control. So trying to get continuity starts when we begin to connect the wall to the roof, the wall to the floor slab, and some of the most challenging details that we need to work out is how do we insert a pre-made component like a window into our wall and connect the air control to the water and the water control and the thermal control. How do we make it continuous across all those transitions? If you're making a building that achieves that, you end up with a very high performance building, one that requires very little energy to operate, one that is exceedingly durable, and one that can have very good indoor air quality. So this is why this approach would be applied across, as I said, many different building types, many different climate zones. So let me get into a few of the more three-dimensional details. The support structure, I've advocated for lightweight wood frames and steel frames, but you can use masonry or you can use reinforced concrete. People have even used things like adobe and rammed earth as the support structure. And into that support structure, we often have to put columns of steel or concrete or wood. But all of that is just wrapped to make it flat. You don't have to do anything with cement, concrete masonry or brick masonry or concrete, but you do with wood and steel frames. Then we apply the layers on the outside. You add the air barrier, the water barrier, thermal insulation, and then wrap it around with the cladding of your choice, shown as brick masonry here. But it's not just about brick masonry. One of the key features of this approach is that you can use pretty much any cladding you want. There are ways of putting on pretty much every cladding that you can think of on the outside of the insulation and the air-water membrane. So yes, this often requires different detailing, different approaches. That's where the work really comes in, is the window penetrations and how do I attach my cladding. So as an example, these are some interesting cladding choices which have a bit of three-dimensionality, and you can change color and texture because they are just cladding. Behind this, somewhere between about 2.5 and 8 centimeters behind these panels begins the insulation. And then behind the insulation is the air-water barrier, and behind that is the support structure. And we have the flexibility to change our cladding rapidly around the building. We can make changes without changing the underlying building enclosure. It allows us to make quite complex facade structures. This is all lightweight Rhine zinc cladding on the exterior of the building. The insulation, air and watertight layer is all in the plane of the glazing that you see here. It just continues in a line. So the enclosure's performance layers are all in a straight vertical line, easy to build in an effective way, and then you shape and sculpt the enclosure cladding as you desire. It also means that we can have open jointed cladding, such as on the left in stone, perforated claddings, such as in the two right examples, that allow air, allow water, and sometimes allow sun through. And that just means that we choose our insulation to be able to tolerate that amount of rain and sun. And then behind that insulation is the protected air and water barrier and the support structure. So let's talk about those layers inside that deliver the performance of the enclosure. Many people are used to insulation, thermal insulation, as a product you purchase. But this approach also requires that you consider how you're going to get air and water control. And the air barrier is a critical component of a modern building system. It is one of those functional requirements that is best met by a specifically identified layer in your building enclosure. One of the roles of the air barrier system is to control the air quality inside the building. You don't want to have uncontrolled leaks through cracks and openings because, first of all, the air that goes through cracks and openings in your wall, it has a real risk of being polluted, particularly by dust and mold. But also, you don't know how much air you're getting into that space because it depends on accidental cracks and openings. And so the goal here is make the enclosure, whether it's a roof, a wall, or a floor slab, as airtight as possible, and then design a controlled and cleanable air pathway, whether by mechanical systems or operable openings. Now, by keeping the air indoors inside during the wintertime, of course, we save energy. But similarly, in the summertime, with the amount of air conditioning, we're keeping not just the heat inside, but the humidity inside. And for insulated buildings, getting good air tightness as an energy and therefore carbon saving strategy can't be underestimated. As we saw buildings be required to be better insulated in the 80s and 90s in North America, we found that the lack of air tightness began to become a major and sometimes the largest source of energy consumption in buildings. And so this is why now we have enacted requirements for air tightness that go alongside the requirements for thermal insulation to drive down energy consumption and drive up indoor air quality and thermal comfort of the occupants. So here are a couple examples of membranes that are air and water tight. They are like your skin. In fact, these ones in particular are also vapor open. So like your skin, they can allow water vapor through while remaining air and water tight. And so these are very common products. A key feature is that they have adhesive on the back side. And so they are stuck to the underlying layers, and that gives them strength and higher performance. Now, that was a picture of just the air and water membrane. Here you can see a building being constructed where we're putting the air and water membrane on. That's the white and blue. Then we're adding insulation on the outside. That would be stone wool type insulation. And then we have our high density laminate, Prodema in this case, cladding being installed over the insulation. But that air-water membrane is entirely integrated with the roof above and with the strip of curtain wall that's installed in between. And that continuity is critical to successful performance. Now, air barriers and water barriers, we'll talk about shortly. It's critical that you understand that you can't purchase a material that will deliver an airtight building. You really have to take the materials and components like windows and doors and combine them together with accessories like tapes, gaskets, and sealants to make a continuous air barrier that wraps the building from the lowest floor that's occupied on the underside all the way to the very top of the roof. So there are various accessories that are needed to be able to get this continuity. And there are a bunch of choices, but you have to make them when you have worked out your enclosure details already. And then you start various specifics about, do I use tape? Do I use sealant? And often that will be a discussion you have in conjunction with your contractor and trade suppliers. So I see here that I was given a question by someone about polycarbonate polycarbonate, or Lexan is a trade name, sheets have begun to be preferred on the facade, and a number of examples have started to increase. How do you evaluate this in terms of environment and insulation? Well, couple things. From an the first question is difficult, the environmental impact. The last question is easy. It has essentially no benefit from a thermal performance point of view. To achieve reasonable thermal resistance, one needs to use an insulating material of a meaningful thickness. Usually those by thicknesses that are reasonable, I'm talking 10 centimeters would be quite appropriate for a climate such as Ankara. So, thin layers just can't make a difference. That is meaningful. The environment, it's difficult. But one of the challenges, there's two challenges with Lexan or polycarbonate claddings. One challenge is that it burns. And so in taller buildings in particular, you will be restricted by fire safety reasons for using polycarbonate. They can make additives to reduce the rate at which it burns, but it still burns. The other challenge is how long will it last? And polycarbonates exposed to the sun, you might get 25 or 30 years out of them. But in comparison to what most people are looking for in their buildings, which is 50 years and up for cladding, it's really on the low end of that. And so the concrete question, I'm not quite sure. Concrete carriers, what kind of insulation difference is there in the ground floor? Actually, this is an important question. Whether they're using wood or concrete as their main structural column and slabs is irrelevant. It does not matter. The layers of insulation I show in those drawings, they are designed to continue past every column, every floor slab. And it doesn't matter if it's made out of steel, concrete, or wood, because you're putting that 10 centimeter, or in some cases as much as 20 centimeters of insulation completely around it. The polar bear doesn't allow any of its bones to stick through its furs. That is the same strategy to apply to your building design. So what is the function of the facade covering is asked? Well, actually, as I mentioned, one thing is it's aesthetics. Let's not kid ourselves. How the building looks matters. However, in most cases, the role of that facade covering is to stop the sun from passing through, maybe to deal with insects, and in urban areas to prevent people from damaging it, or being cleanable and repairable against graffiti and so on. So it's not to stop air. It's not to stop water, it's not to stop heat, and it's not to hold up the floors or resist wind load. It is to do those other things of making an exterior finish that is able to withstand the rigors of exposure and keep looking good. So I've mentioned air, and now I want to mention rain, because rain is the biggest reason we get big problems in buildings. So these are problems that the owner calls you up and complains about: water leaking through the roof, mold growing below the window, etc. And so stopping rain leakage is as important as stopping air leakage. The approach taken, and this goes a bit to the question about the role of the facade, is that the approach promoted for most assemblies, and certainly the one I'm describing, is that the cladding is a screen to rain. It is not a barrier to rain. Sure, it sheds water off, but the assumption is that water is going to leak through at joints between panel components and around windows and around balconies and so on. And therefore, we accept that and we provide a gap to allow drainage, sometimes several gaps, and we install that air and water control layer. The water resistive barrier is the language you will find used in North America. But that layer of water control is often integrated with the air control. So you only have to buy and install one product, but it does both the air and the rain. And this is critical in terms of the performance. This is why it allows us to have perforated claddings, different styles of claddings that meet in different ways. Now, here's an extreme example, which actually goes back to the question about what's the main function of the facade covering. This is a very exotic building shape and form, and it happens to be in Denver, Colorado. And those panels are made of fiber cement. There's skylights in them. The joints between those panels are actually open. And so here we have an extreme example of when I said the wall and the roof are essentially the same concept. Well, here we have a combined wall and roof design. But because of the open joints and the fact that it's sloped, often we need to use an additional layer of water control on the outside of the insulation. So when we go from the vertical to the sloped, we'll sometimes add another layer. And again, we're not expecting that outer layer to be perfect in terms of stopping rainwater getting into the assembly, but it so reduces the amount of water that gets into the assembly that the lower level, the skin underneath the insulation, performs the function of being a full air and water backup. So I call this the same approach plus. Now, because the joints in the cladding are open, one of the things that matters is that we now need that layer to be sun resistant, UV resistant. And remarkably, we have products that can do that. We even can change that lower layer that's seen through the joints. You can get a whole range of interesting colors if that also works with the architecture. So one of the questions is, what is the effect of these materials on human health? Well, it's entirely dependent on which materials we're talking about. There are hundreds of different materials available. What we do know is that, for example, using lots of uninsulated buildings with no airtight, we know the effects of that on human health. We are expecting millions of people to die because of climate change. And so what we do know is that that's probably not going to be an answer going forward. But some of these products are made of and increasingly as people ask those tough questions of manufacturers, we see these materials being made more ecologically healthy. In terms of human health, very few effects on human health directly. You know, that's why they're used by literally hundreds of millions of people throughout all of Europe, Southeast Asia, North America. So when we look at these principles applied to a little bit more detail, so this is why I want to say we're getting to just the nitty-gritty. I'm showing you a clay brick veneer. So for example, one of the challenges with clay brick veneer is that it uses a lot of energy to fire the clay. So depending on the standard you wish to apply, brick is a horribly environmental building material, partly because most of the way we make brick is with high carbon furnaces. So we emit a lot of carbon before we even construct the building. The amount of carbon that's in the steel stud support structure, by the way, is significantly less by usually factors of 5 and 10. And if you can look up rating systems for also the effect on water quality, particulate emissions, habitat destruction. And although brick is a traditional material, which is quite durable and has a lot going for it, from an environmental standpoint, when one looks at it rationally rather than from a nostalgia point of view, it doesn't look very good. Now, steel has a lot of carbon in it, but steel studs, we use so little steel because they're so structurally efficient that actually it performs relatively well. And this is the kind of questioning we're getting on real projects, but it depends on, are you working on a large, let's say, school where you need to meet local codes and standards, you don't have as many options to make. I've certainly worked on projects where in rural America, where we have used, as an example, earth plastered straw bale, very environmentally friendly materials, but very impossible to build a 3-story building of in downtown Chicago. There's too many other performance requirements, and one has to balance the living in urban areas and the environmental benefits that has versus the material choices and the performance that demands. So this is just an example of a real life building assembly that works and is not uncommon. I want to emphasize here that these types of concepts are not uncommon. They are being built in the thousands of buildings every year. And if you execute properly these continuity of layers and insulation, you can get incredibly high performance from a point of view of operational energy. From a point of view of carbon sequestration, how much energy, how much carbon is emitted by the manufacture of the material shown, that's sort of a newer concern. But we are doing this on buildings. It is a question being asked: what are the carbon emissions? What are the resource depletion issues with this assembly versus another assembly? And as we work through that, you really do have to follow the science and the facts, not assume that this material is natural and therefore not bad for the environment. This material is man-made and therefore it's bad for the environment. So last sort of topic I want to raise here is green and walkable roofs. Perhaps we've noticed more than before, but in COVID times, when we were not able to leave our buildings and go to seaside resorts, or perhaps meet in public squares, the ability to have outdoor surfaces that you can use yourself or you and your family have become that much more valuable. But those same surfaces are highly valuable in any time, whether you're in the middle of a global pandemic or not. And this is what I think is a great project that demonstrates the buildings cascading down a sloped environment. On the upper left, we see there's a balcony, hard surface, you can walk on it. And then the green, where probably you can walk on it as well, but it'll be, a little bit dirtier when it's wet and so on. But it has a great combination of creating private space that allows you to be outdoors. So these green and walkable roofs are becoming more important than ever. And I think that we're going to see more of them as we urbanize. The concept of a green roof doesn't have much meaning if you're building the only house in 500 meters. You have all that, the potential of gardens around you. But as we build in higher density, very much for environmental benefit reasons, we put buildings closer together, these types of spaces become more useful. Now, I'd introduced the general arrangement of materials earlier. Protected membrane roofs, or PMRs, is the technical description. Sometimes an old label was the inverted roof, and it was inverted versus how they used to do it. But from a building science, from the physics of how buildings work, this is the right way, not the inverted way. The roof membrane is put over top of the support structure. A drainage layer is provided below the insulation so that any water that gets down to the level of insulation can be drained away harmlessly. And we often have to use special layers to store moisture for the soil plants above and prevent any of the dirt particles from the soil washing away into the roof. So green roof details here, I'll show you just a little bit more elaboration of what they can look like. This happens to use a precast structural concrete deck. But then there's a roof membrane called a drainage plane because the water drains along that. Then there's a drainage gap, insulation, etc. Now I'm showing you on the left, it's a green roof, and then we have a curb in the middle, a separator, a piece of concrete or stone, and then we have some sort of gravel surface, just to indicate that you can change what the top surface of this assembly looks like. It can be green, it could be gravel is the lowest cost way, or it can also be pavers or wood sleepers to create a walkable roof. But the design is very much the same approach. It's just that when we have green space above, there is a benefit to storing some water in that upper layer to feed those green plants in between rainfalls. Whereas when we're using a walkable surface, we don't try and save the water. We try and drain it away quickly. But the concept of support structure, air-water membrane, insulation, and exterior cladding works beautifully around low-slope roofs, from allowing us to do green roofs, decorative stone, walking surfaces of tiles, concrete, and wood. So let me just wrap up some of these conclusions. Our polar bear is an indicator of how one would approach the building science of building enclosures, is an appropriate icon today, not because the polar bear represents the climate that most people are focused on, but because the way we're building now is changing the climate so that we're destroying the polar bears. And you can see he's praying for you to change your ways, choose different materials and arrangements as a way of responding to the demands of changing climates, while we also continue to make good interior spaces that are useful and comfortable and hopefully beautiful and satisfying on the outside. So with that, I'm going to go spend more time looking at the questions. I see I got a question about what is the positive of these types of air and water to sound insulation. Good question. Now, from a sound insulation point of view, being airtight is very significant. Many of you may have experienced the idea or had the experience of being in a building when all that what happened in a city was latched. It didn't look like it was open, but it was unlatched. You go over and you close that window tightly, make it airtight, and you end up with much better sound control. And so there's a real benefit to getting good sound control by having good air control.
Okay, thank you very much, Mr. Straube, for the very informative and detailed presentation. It seems very clear that as architects, we need to reconsider our choices for structural systems, building enclosures, and insulation materials and their layers as well.